figure 12. Now, instantaneous dipole we covered last time, so we need to crank up the strength a little. We start talking about permanent dipoles. Now, we've had permanent dipoles in molecules before. We know that it is driven by electronegative atoms. So when you look at the top right hand corner of the periodic table, all those non-metals, they are electronegative. They pull electrons towards themselves, creating a deficit of negative, meaning a positive, at the other end of the bond, or possibly at the other end of the molecule if it's quite a strong pull. Now, I've written up there PD, ID. ID is induced dipole, like last time. But now it's caused by a permanent dipole. Now, the permanent dipole is a stronger dipole than one of those instantaneous dipoles. So therefore, if you have a molecule that is not, oh dear, we don't know what that chemical element is because we've gone a little crazy with the pen. Hang on a second. That's a little more convincing as a chlorine. There we go, chlorine molecule. Now, we need something that'll have a permanent dipole, HCl molecules. There we go. So, HCl, chlorine is the electronegative atom out of those two, up in the right hand end of the periodic table, fairly up the top. Permanent dipole, negative on the chlorine. Putting this nearby will mean it will induce, I'm using a dotty thing, I just don't know whether that's a sensible thing, but there's like a dotty thing there. For the causing, negative will mean it will do that and it will do that. Now, how could you explain that? Well, delta negative there, more negative charge, more electrons therefore, will push the electrons away in the chlorine molecule, so the negatives will end up away from the negatives there. And that positive is then attracted back to the chlorine. So therefore you have a stronger attraction than the ID, the instantaneous induced one from last time. Not massively stronger, but it is stronger. So you find something that's non-polar, and there are lots of examples. Methane is non-polar, and it will have an induced dipole caused by polarized bonds. On the other hand, it's not as strong as what we're going to go to now, which is much more common to have questions about, if I'm honest, which is permanent dipole, permanent dipole. So here you get two molecules with an electronegative atom, permanent dipole caused by that. Now, firstly, you can consider just two things that are the same. So you could have HCl, HCl. Delta negative is the same idea as above, it's just that there's no induction going on to cause an induced dipole now. That dipole is a permanent feature. There will be those bonds. You put it in the gas phase, it doesn't do it. There's too much energy to have that bond. It has broken all of that, and that's how you get things to be a gas, is you break these attractions. So in this case you break the permanent dipole, permanent dipole. Hydrogen chloride is a gas at room temperature, so that is not very strong because the thermal energy of a room is enough to cause HCl to be a gas. In fact, it would do it well below freezing point. It's not that strong an attraction. But you can do it between two things that are the same. You could do it with a more complicated molecule, something like, well, look. Chloroethene, what's used to make PVC, because the monomer for PVC. It would be delta negative there, delta plus there. Now there is a thing about the double bond being delta negative as well, but you do that and it will then go, alright, there's the delta plus on delta minus. There's the attraction between the chlorine and the carbon delta plus there. So you will get permanent dipole attracting permanent dipole. Those are two examples of the molecule attracting its neighbouring molecule that is the same. However, it's not restricted to that. So I'll take this one out of the way because it's a bit of a clutter. Now if we take that out of the way and you go and pick a different molecule, now here's an example of a molecule that's got 3 electronegative atoms. So these things are dragging electric charge towards them, and that means that actually the hydrogen ends up delta plus and then all of these are delta minus. And that will mean you get the attraction from the chlorine of the HCl to the hydrogen of the trichloromethane. Two different molecules attracting. Now what that means is that hydrogen chloride is quite likely to dissolve in trichloromethane. Quite likely to have some solubility. Doesn't tell you how soluble, but it does tell you that there's a reason for it dissolving. Now the sort of questions you can get asked is draw an interaction between two molecules that explain why whichever one dissolves in whichever one out of the pair. And of course it will work in either direction if they're both liquids. So you get this idea of substances dissolving in others, explained by this. You also get the idea of liquids mixing with each other, which is kind of the same idea as things dissolving in each other. But you call it miscibility, which is, I think it's a word we've met before. But miscible is for two liquids that, well, you get the two mixing together. You don't get the two-layer separation thing like you do with oil and water. So you get that explanation. Now there are loads of polarised molecules. Here's a, I'm just going to get rid of that as well because it's a bit in the way. So when you get that feature, which is something we'll meet at some point in the not too distant future with these things, that's what's called a carbonyl. Carbonyl is polarised like that. The oxygen is the electronegative. It's up the top corner of the periodic table. This is a very familiar molecule to many chemists. It's called propanone, and it's got that permanent feature of a dipole. And you put that with something else. Now this is a molecule that I have to say, oh dear, we have to say is not something we study the chemistry of, although it does get a mention in the Salters course. There's a thing called an ether. Oxygen, delta minus, be a delta plus on those. They won't be so big as the oxygen's delta minus, because the delta minus is split to two dipoles going to the left and the right, but there's your interaction. That is a liquid at room temperature, that is a liquid at room temperature. They are likely to be miscible, mixing together, the word that's gone. So you can explain solubility. You can have to write drawings of two molecules, permanent dipoles, lined up in the correct orientation, because this is all about the orientation. And that's kind of it when it comes to permanent dipoles, except for the one special thing that we're saving for the next time, because it's the favourite one for exam questions. And it's the favourite of biologists because it's a thing about lots of biological molecules and enzymes and protein structures is hydrogen bonding. Hydrogen bonding is a very special form of permanent dipole that is significantly stronger, and we will cover that in a special session that's going to follow, not immediately because we haven't filmed it yet. So thank you very much for watching, and there will be obviously some questions attached to this that you need to do, but I look forward to hearing your comments and leaving your responses. Thank you very much. Bye.